Assalamu alaikum, dear student. This is the lecture number 1 of week number 14. This is the continuation of the lecture of chapter number 5. So we have chosen a topic from the chapter number 5 is the linear moment, conservation of linear momentum. And we have already discussed about the impulse of free jet, okay, and we learned that how to calculate the impulse force acting on the fixed and moving blades. Now we are going to start the revision of the topic when the pipe is flowing through the pipe bends or through the pipe. So how the impulse uh, how the impulse generated due to the change in direction of fluid flow, okay, so the and how we can calculate the force of impulse and the reactive force to anchor the pipe bed. Okay, so the topics we are going to cover today: the conservation of linear momentum and the fluid flow through pipe bends. Okay, and the practice problems. Obviously, we will do that. So mainly we are focusing on the practice problem, that how we can calculate the the anchoring force uh, to anchor the pipe bend when fluid is flowing through the pipe bends. Okay, so previously we have discussed this slide in video lecture number 3 of week number 6. So just I will give you a quick review. You see, the purpose of studying this topic is to provide how to calculate the anchoring force to hold the pipe bed. Okay, this is basically practically it is very important that I will show to you the pictures and others. So as you can see here, it is written the flow through the pipe bends. The component of the anchoring force, okay, the the component of the anchoring force to hold the pipe bend, okay, in place, the horizontal forces acting on the content of this control volume are identified in figures. Okay, so these dotted lines are basically indicating the control lines and how the calculation changes, okay, when we change the control volume. Okay, so this we can see. So weight of the water is vertical in the negative z direction. This is the weight of the water is showing here. Okay, this is the weight of the water. Okay, uh, all right. So the all the horizontal, normal and tangential forces exert on the fluid and the pipe bend are resolved and combined into the two resultant components, FAX and FAY. These two forces act on the control volume contents and thus for the x direction and shown. So here you see in the first case here, quickly I will review and then I will go back to the practice problem so the concept will be more clear. Okay. So you see here we are considering the pipe bend and the water together. Okay, so here you see what happens when the fluid flow through the pipe. Okay, so definitely because of the change in direction, the velocity changes. The direction is changing, that means the velocity is changing. So because of that, a fluid exerts a strong force at this point, okay, or at the surface of this point. Okay, so here is we are considering the maximum force is acting at this particular point. Okay, there is a force on the different point also, because the velocity is continuously changing its direction, so because of that the momentum is changing. Okay, so but this is the point where where the force is maximum. Okay, so this force exerted by the fluid is indicating by FAY. Okay, FAY. And the vertical component is FAZ and the X direction is FAX. Okay, so we have learned that according to the second law of motion, okay, the net force acting on the object or by the object, or net force exerted by the fluid or on the fluid is equal to the change in momentum. Okay, or the rate of change of momentum, sorry, the rate of change of momentum. So here you can see uh, the net force. This is basically, we are considering this is X direction. Okay, here it is mentioned, and this is your Y direction, and this is your Z direction. So first we have considered net force acting in the X direction. Okay, so what is the net force acting in the X direction? So this is our direction of X. So what are the forces acting in the X direction? Nothing, only the X component of the resultant force. So that means there is no other external force components are acting on this X direction. So that's why Fx we are considering is equals to 0. Okay, the mass flow rate is same. Okay, because the dia is not changing, or even the one inlet and one outlet. Okay, because since the one inlet and one outlet we have, so the mass flow rate is not changing. Okay. Second, so this is the equation for the y component. So we can see the net force acting in the y direction is equal to rate of change of momentum. Okay, so what are the net force acting in the y direction? So this is our positive. Basically this is the vector sum, huh? So we have to take care of the sign because of its direction, and this is the negative direction, okay, of the y. This is negative and this is positive. Okay, so here we are considering the acting, uh, net force exerted by the fluid, okay, on the surface of the elbow. Okay, so here, so what are the net external forces? So one is basically the net force that we want to calculate, that is FAX, okay, on the surface of the elbow. And second, the force exerted due to change in pressure, because this is the driving force. Because of that the fluid is flowing through the pipe. Okay, so we know that the force is equals to P into A. So this is the pressure force and this is the inlet point. So inlet point is basically in the in the positive y direction. So we consider P1 A1, or here we are consider P2 A2. This is also in the positive X direction. Okay, and this we have also considering the force is exerting on this surface by the fluid. Okay, so here P2A2. Now the change in momentum. So what is the rate of change of momentum? M dot V2 minus V1. Okay, M dot V2 minus V1. So what is V2? V2, you see, it is opposite to the positive y direction, so we consider it is negative. Okay, and plus mass flow rate. Okay, so here uh, what minus, okay, minus m dot v1. So here v1 is positive, you can see. So we consider v1 is positive, and the minus sign we have taken inside. So this has become minus m dot 1. Okay, so this is how we make the equation of the force exerted by the fluid, or the force exerted, or the reactive force exerted by the uh, surface of elbow on the fluid. Okay, so here you see we have considered another sketch. In this sketch you can see we have taken only water. This is basically a water, and this is our control volume. Okay, so all the forces which are acting on the water we have mentioned. This is the pressure force and the velocities. Okay, and this is the force, basically the reactive force, which basically the fluid exerts, okay, on the surface. So this is the reactive force, but this is the force what exactly the fluid exerts on the surface of the wall. So the magnitude is going to be Ry, but the direction is same. This is the direction of the fluid, and the magnitude is exactly same as the force exerted by the solid surface of the pipe band. Okay, so that's why it is mentioning here. So if you open up, you will end up with the same equation. Okay, because you see if you take this one other side, okay, so this will become, take minus common, to minus m dot v1 plus v2, and same minus p1 a1, and this is minus p2 a2, then ry will become equal to this. Okay, so these two are almost the same equation. Okay, here, in the third picture, we can see the pipe bend only. Here we are considering only pipe bend, which basically give resistance to the fluid flow. Okay, so if we are considering the pipe bend, to hold this pipe bend, if the fluid is flowing through it, to hold this pipe bend, we need a reactive force, and that reactive force, okay, that can give resistance to this fluid flow, that will be equal to 1. Is this is the reactive force that we need, okay, to hold this pipe, and this is the atmospheric pressure which always there to give resistance uh, to the flow, okay, or to the pipe. Okay, because if we do not provide any support, and the force is strong enough, so what will happen, it will move. So to hold it, we need an equivalent reactive force, that is basically Ry, and this external force is always there. Okay, so these two forces basically always equal and opposite, okay, to the force exerted by the fluid. So this is the force exerted by the fluid, and this is basically the anchoring force that we have to calculate. So this FAY basically give you the magnitude of the anchoring force that we have to take care of it. So this is the force we have calculated exerted by the fluid, and this is the force, okay, given by the atmospheric pressure. Okay, so this is how we calculate the force exerted by the fluid, or the anchoring force to hold the pipe. So let's view some pictures. So this is some pictures from the field. Okay, so here I have taken a straight pipe, and you can see some nuts and bolts here. Okay, sorry, these are the fasteners. Okay, it's nuts and bolts. This is basically the rivets, the very strong rivets, and these are the joints you can see here. Okay, and here also you can see the pipe bends, and this is basically a pump. Okay, because whenever the pump discharge water through this point, what happened, there is a strong force exerts here. So if you will not provide a strong support, what will happen, it may bulge or move right and left and may damage. Okay, so we provide an anchoring force at this point. So how strong this anchoring force supposed to be, we have just seen that how we can calculate this anchoring force. Okay, so these are the nuts and bolts also. Okay, so basically, because of the change in pressure, there is also a force on the nuts and bolts. So these nuts and bolts are also calculated precisely, that if this is the inlet and exit pressure, so how much strong supposed to be these nuts and bolts. Okay. So here you see these are the elbows, and you can see here in the picture, okay, there are supports, okay, to hold the elbow, and also you see these are standard design, okay, elbow with the anchoring supports, okay. So these are the anchoring supports. So this is basically is the large radius. When there is a large radius, that means we by increasing the large radius we can reduce the force exerted by the fluid, and we in that case we need a less reactive force or anchoring support. If there is a short radius, okay, that means there will be a more pressure drop, and there will be a more stronger force on the elbow. So in that case, we have strong anchoring supports. Okay. So the and here also you can see the rivets, okay, because whenever the fluid flows, because of the change in momentum, okay, what happen because of the change in momentum, there is because of the pressure force, okay, there is stresses on these rivets, okay. If these rivets are not strong enough, what will happen? There will be possible leakage from these points, or it will may break from here, okay. So that's why we do these whenever the fluid flows through the pipe, so these all joints comes under stress, okay. So these the size of these rivets, the size of the elbows, the size of the nuts and bolts, and the size of the couplings, all are must be must be installed according to the standard pressure class. Okay, so this is basically a very practical. We see what is the pressure class, and based on that we select the size of the rivet, size of the nuts and bolts, size of the flanges. Okay, so these are, you can see, these are basically the flanges. If you can see, this is the flanges. These joints are called Victaulic joints. Okay, so here you see this is basically the flangent. This is flanges. Okay, we do have holes here to fasten them with the nuts and bolts. You can see here this is also these are also flanges. Okay, these are also flanges, and these are fastened with the nuts and bolts. Okay, these are flange joints. Okay, and these supports are anchored with the floor, okay, to hold the uh, to anchor the elbow. Okay, so now let's calculate, let's do some practical examples. So here a pipe with a cross-sectional area of A has a 90-degree bend. Okay, so this is basically the elbow you can see here. If water travels in the pipe with a velocity of v, so this is the velocity v, water is and coming through a pipe. Okay, suppose this is a pipe. Okay, so water is coming all the way through a pipe. Okay, so when it enters to the elbow, at that time the velocity is v1. Okay, the velocity, this is the pipe. Okay, and the velocity is v1. So when the water reaches to the elbows cross section, at that time the velocity of the fluid is v1, and the pressure at this cross section is p1a1. Okay, so the pressure force we are saying here is f1. Okay, so after going all the way from the elbow, okay, the velocity becomes v2 because it changes direction. Okay, and the pressure force, okay, it become p2a2, which is equal to f2. Okay, and the force exerted by the fluid on the elbow, okay, to hold it we need an anchoring force. Okay, so we need an anchoring force that is basically rx and ry. So how strong this anchor or support to be to hold this elbow. Okay, so here uh, so if the water travels in the pipe with a velocity of v and the density of the water is d, so what is the force acting on the pipe bend? Okay, so whatever the force, what is the force acting on the bend of the pipe? So what are the forces acting on the bend of the pipe? So this is the bend of the pipe. So we are going to calculate the force on the bend of the pipe. So this is the reactive force, okay, against the fluid flow, okay, to anchor this elbow. So let's analyze one by one. So here we will assume that this is a constant diameter elbow. Okay, sometimes we use a reduced elbow because at the what is the meaning of reduced elbow? So if the diameter is d1 here, if the diameter is d, okay, what is if the diameter is d, so if it is a uh, if it is a uniform diameter elbow or same diameter elbow, so diameter going to be d here. But if it is a reduced elbow, so if the diameter at the inlet is d, so diameter at the discharge will be small d. Okay, so this is going to be a something different, something like this. The discharge dia will be reduced instead of this point. Okay. So here we will assume that this is a constant diameter elbow. The diameter of the elbow is not changing or not reducing. So the fluid velocity is V1 is equals to V2. Since the area is same, so Q is equals to Q1 is equals to Q2. So if the area is same, then in that case V1 will be equal to V2. Okay. So also if we neglect pressure loss around the elbow, then P1 will be equal to P2. Okay. If we are considering there is no friction loss, okay, through the elbow, there is no pressure drop through the elbow. Okay, as we have learned in the chapter number 8 that there is a pressure drop. But here we are assuming if there is no pressure, sorry, if there is no friction loss through the elbow, is smooth. So what will happen? The P1 will be equal to P2. Okay, so note that the force from the fluid acts on the right on the actual elbow. So the reaction force acts equal and opposite to the left on the fluid as shown in figure. Okay, so here we can see, okay, because you see if the fluid is acting exerting force in this direction, okay, so okay, this is the fluid force, net force, Fx, force in the x direction and force in the y direction. Okay. So this is the force exerted by the, so the magnitude is going to be the same, but the direction will be opposite. Okay. So this what we are saying here, and this reactive force is equal to Rx, equal opposite to the left on the fluid as shown. Okay, simply write Newton's second law in the x direction. So according to the second law of Newton, sigma force is equals to rate of change of momentum. Okay, so rate of change of uh, momentum. So sigma force is equals to in x direction. Okay, is equals to mass into rate of change of momentum. Okay, sorry, rate of change, acceleration can be written in the form of rate of change of velocity, and then this will become, okay, move this delta t from here to here, and this is going to be change in velocity. So this is equation 1. So but we know that mass flow rate over time, okay, will be equal to the mass flow rate, that will be equal to rho va. Okay, so where q is equals to mass flow rate, this is density, and this is flow area or the cross section area. Okay, So here, this is the sketch, and all the forces you can see which are acting on the elbow due to the fluid. Okay, so equation one become. So now if you do equation one, sigma fx is equals to, we replace mass flow rate with rho va, and then change in velocity in x direction. So what is the velocity in x direction? V1x, sorry, V2 minus V1. So V2 minus x minus V1 minus x. So this is our x direction, okay, and this is our y direction. So we will solve it. Okay. So this is basically the basic equation. Okay. All the forces acting in the x direction. So we are going to resolve. So if we expand, so this equation will become like this. Okay. So here, so V2x, what is a V2x? So this is the direction of V2. Okay. This is the direction of, this is point 1, because this is section 1 and this is section 2. So at section 2, do you see any velocity in x direction? Do you see any velocity in this direction? No. So that's why V2x is going to be 0. So do you see any velocity at point 1 in x direction? Yes, that is V1x. That is equal to V1 or V. Okay. So this, so we're gonna put these values here. Okay, so what is this, is this will be equal to 0, this will be equal to 0, and this will be equal to v, so that will become minus v. So sigma fx will become minus rho v square a. Now the only two force acting in the x direction, one our free body diagram, on our free diagram, are Rx and the force due to fluid pressure F1 and Fx. So there was a two component of equation 1. Okay, one is the momentum side and other is the force side. So here we are talking about, what about sigma x? So what are the forces acting in x direction? Okay, so we resolved the momentum part. Now we are trying to find the value of sigma fx. So what are the forces acting in the x direction? So the net force, to what are the forces according to the free body diagram in x direction? We can see there is a Rx and there is a pressure force. Okay, at point 1. At point 1 we have pressure force. At point 2 we do not have any force in the x direction. So we have a two forces, F1 and Rx. So sigma Fx. So now see the direction of these forces. So this is also positive and Rx is negative. So P1 A minus Rx is equals to minus rho V square A. Okay. So we replace this Fx with these two forces, and Rx is negative because it is opposite to the x direction, or opposite to the direction of fluid flow. Okay, so here Rx will be equal to P1A plus rho V square A. So this is the equation, this is the value of reactive force in x direction that we have calculated. Okay, so we replace the density with T as we have as it was given in the problem. Okay, so now we are going to resolve the forces in y direction. Okay, so remember that this is the force acting on the fluid, since we used a free body diagram of the fluid. Okay, remember that this is the force acting on the fluid, since we used a free body diagram of the fluid. Okay, so the direction of the force on the elbow will be opposite to that shown in my free body diagram. Okay, so here it is mentioned according to the Newton's law. Okay, let's analyze in the equation all the forces acting in y direction. Okay, so this is the same that we have done for the x. Okay, these are the values okay, that we have already calculated. So the sigma equation 2 become, okay, so this is the equation 2. So this will be replaced with the rho va. Okay, and V1y is equals to 0. So is there any y component in the at point 1? No. Only there is x component, so there is no y component. That's why V1 y is going to be 0. Okay, so this component will be going to be 0. Okay, V2y and sorry. Uh, at point 1. So this component will be 0. Okay, this component will be 0, and let me delete this for you. Okay, so that component will be 0. Okay, that component will be 0, and V2 is equals to, what is V2y? At V2 we have a velocity in the y positive y direction, so this is going to be V. So the, sigma Fy will be equal to rho AV. Now we are going to analyze net force acting in the y direction. So the net force acting in the y direction, there is one y which is in the positive direction, and there is a pressure force in the downward negative direction. So this is going to be Ry is positive, okay, sigma Fy, Ry is positive minus, this is down, equal to this. And this we have calculated already, that is rho V square A. So we replace this. So Ry will become P2A plus rho V square A. So now this is the final Ry value. So these are the two anchoring force that we have to calculate it. Okay. Now the net resultant force. So what is the net resultant force of these two that we can calculate, and what is the angle of this net resultant force that we can calculate by equation which is given. R is equals to Rx square and Ry square. Put the values and finally you will end up this result. Okay. And if you simplify further with the different angles and everything, so you will end up with this equation finally. Okay. So this is the, so if there is no loss, here is saying the condition is giving, okay, because if there is no loss, okay, in the elbow, so the P1 will be equal to P2, so we can replace P1, P2 with the P, and finally the resultant anchoring force will be equal to this component. Thank you very much.